Myself R.V. Gudi, working as physics lecturer in RLS PU College, Belagavi. Today I am here to explain you how to find the focal length of convex lens. As we know, focal length is the distance between optic center and principal focus. How do we define principal focus? When parallel rays of light are incident on one surface of the lens, after the refraction, all the refracted rays will converge or actually meet at one point on the principal axis. So this point we call it as principal focus. So now here, to start with the experiment, the object distance should be more than focal length and less than 2 times of the focal length. First step is to find the approximate focal length of the given convex lens. So for that, take any distant object. So now here I am taking trees and buildings as my distant objects. I just adjust the lens position where I get the clear image of the object. That is, that distance I have to measure, and that becomes my approximate focal length. So here, as you all can see, I am getting a clear inverted image of the trees and buildings. So this is my approximate focal length, and this distance I have to measure from the lens. So this distance I am getting it as this distance, as you can see, it is from this line to this line. So it is a 12 centimeter. Now lens, convex lens, we have mounted it. This is the optical bench and convex lens is mounted on the lens holder or lens stand. Here the optical bench is of 1 meter or 100 centimeter, and we are fixing the lens position at 50 centimeter. Object pin distance should be more than focal length and less than 2 times of the focal length. It's okay if we measure anyhow we have measured the focal length as 12 centimeter. We can also start taking 2 times of 12 is 24 centimeter. So in the neighborhood of 24 centimeter, we can start taking the readings. So 25, 26, 25, 24, 23, 22 centimeter, that method also is fine, no problem. But now here the first step is to get the inverted image of the object. So here at 14 centimeter, the image was highly magnified, and now I have fixed the object distance at 15 centimeter from the lens, and here you can see the inverted image of the object. Now I mount the image pen by adjusting the height suitably so that the inverted image of the image pen coincides with the tip of this image pen. Now they are not in the same line. Inverted image is towards the right of this pin. So to adjust them in a line, I use this fine adjustment screw and move it properly so that they are aligned. This alignment we need to do only for first reading. Now to eliminate the parallax means when I move my eye left and right, image pin and the inverted image are moving separately. So they should move together. So to eliminate the parallax, I have to adjust this distance between image pin and the lens. Now I am moving the image pin closer to the lens, and at one point they will coincide. So here separation goes on decreasing, and at one point they coincide. So here we can see that the image pin and the inverted image are coinciding exactly, and they are moving together. So there is no parallax. So this distance between the lens and image pin is image distance. Distance between object pin and the lens is object distance. Now you can see inverted image of the object pin is exactly coinciding with the image pin, and there is no parallax also. As you can see, object pin is at 65 centimeter and lens is mounted at 50. So 65 minus 50 will give us object distance, which is 15 centimeters. And here we can see image pin is at 19 centimeter. 50 minus 19 centimeter will give us image distance, which is 31 centimeters. Now by increasing the object distance by 1 centimeter or 1.5 centimeter, we have to adjust the image pin without parallax and that distance becomes image distance. So I have increased here by 1 centimeter, and now I have to adjust the image distance. Again, by closing one eye, we are adjusting the image pin so that there is no parallax. Just move our eye left and right so that we can see there is no parallax. So here we can see that again at this distance there is no parallax. Now you can see inverted image of the object pin is exactly coinciding with the image pin, and there is no parallax also. So at 16 centimeter I got this image distance as 28.2 centimeter. In this way, every time by increasing the object distance by 1 centimeter, we have to decrease the image pin or take it closer to the lens, and without parallax, when we adjust that distance we need to note down, and that is image distance. So in this way, take some 5 readings and then plot the graph. I have taken the readings in this way. So by taking the readings, we are plotting the graph in the second quadrant, taking object distance along x-axis and image distance along the y-axis. Here, to find out the focal length of the convex lens, we need to bisect this graph, and it cuts the curve at one point. Corresponding object distance and image distance we need to note down, and focal length is found by measuring these distances. OA plus OB divided by 4, like how I have shown in the graph. So corresponding values of u and v we have written, and finally we found the focal length as 10.4 centimeter. Here we are plotting the graph in the second quadrant because object distance will be negative. If you apply a sign convention, light rays are incident from the object on the lens, whereas all the distances we measure from the optic center. So we are measuring the distance from the optic center to the object pin, which is opposite to the direction of incident rays. So object distance will be always negative, and image distance, if we consider from the optic center to the image pin, which is along the direction of incident rays, so image distance is positive and object distance is negative. Hence the graph will be in the second quadrant.